We'll see. Okay, so we need to identify 3 true statements. There's 2 ways we can do this. We can either come up with 3 true statements or eliminate the ones that are not true, right? So this one is a little bit complex. LEU, THR, ASP, val, ser, arg, glue, 1, 2, 3, 4, 5, 6, 7, is likely repeat in the alpha helix of carotene. Notice the stuff we learned before. 2 alpha helices in a coiled coil. Each helix has a 7 residue repeating unit. Okay, well that makes sense so far with what we know, right? What else could we use to judge the truth of this? Well, we could think about, are those groups that oftentimes show up in an alpha helix? That would be a good place to start, right? Do they make sense to be in what this is used for? So this is an intermediate filament. There you go. And then we look at this, and we have A, B, C, D, E, F, G coming out towards us, right? Okay. And then this is 2 filaments. They're going to be next to each other. We have A, B, C, D, E, F, G coming out towards us. D would interact with A. D here would interact with A, right? So we would want to look, does A and D make sense to interact? A, B, C, D, LEU, BAL. So leucine, hydrophobic group, right? Okay, and then we look at A, B, C, D, val. Hey, valine is also a hydrophobic group. Would it make sense for 2 hydrophobic groups to be near each other and interacting? Yeah, that makes sense, doesn't it? Okay, so that one actually makes some sort of sense. So then we go down. Alpha carotene is rich in cysteine residues, enabling the formation of covalent cross links between peptide chains and increasing the length of the protein. Okay, so what do we know about this? Well, we need to have repeated structural units that are going to attach to each other, right? Would that make sense for that to be true then? Yeah, that makes some sense, doesn't it? That would give you a way to link these up. And so you'd have cross-links between these peptide chains, increasing that strength of the protein. This is a structural protein. Everything about that makes sense, doesn't it? Okay, so each polypeptide in the dimer has 3.6 residues per turn, and a nonpolar group occurs every 3.5 residues, resulting in a slight wind or twist around the other polypeptide, forming a coiled coil. Okay, so we know it's a coiled coil, right? Anybody know what a coiled coil means? They're coils, because they're alpha helices, and then they braid, making it another coil, another layer of coiling. Does that make sense? Yeah. Is everybody okay with that? Okay. I mean, that's how you make rope, right? You take twines, you twine them, and you twine them again, and it gives you more structural support, right? So any failed point doesn't shear right through, right? Okay. Each polypeptide in the dimer, has 3.6 residues per turn. Okay, well, let's see. What is a turn? 1, 2, 3. Not quite a full one there, is it? Because this goes a bit further than this. So that's a bit more than a full turn, isn't it? Okay, that makes sense. 1, 2, 3. Again, that was a bit more than a full turn, wasn't it? Okay, well, okay, 3.6 for a full turn. Oh, okay. Yeah, sure. I could see that. And a nonpolar group occurs every 3.5 residues, resulting in a slight wind or twist. Again, these nonpolar would give you an association point, right? It actually fits in with the previous statement we said was true, by the way. You guys notice that? The two nonpolar groups we looked at being across from each other? Okay, so let's go on to the other. Carotene molecules are very strong due to hydrophilic interactions between charged amino acid side chains. Figuring out the ones that are wrong is pretty damn easy in this case, isn't it? Our charged side chain is going to be hydrophilic, yes, but does it make sense that hydrophilic interactions in water are going to make this structurally support itself? No, because they're surrounded by water, right? You see where that's a problem? Water can get in there, dissolve the damn thing. Wouldn't be a very good structural molecule in water, would it? All right. The residues at positions B and C are less likely to be polar or charged because they are in contact with the solvent. Okay, this one is structurally doesn't make any sense, right? So if you're, okay, so we look at B and C. Here's C, here's B, right? Are those actually less likely to be in contact with the solvent? They're on the outside, aren't they? What should be surrounding this? Water, right? There's probably water surrounding this. So does this make sense? The residues at B and C are less likely to be polar or charged because they are in contact with solvent. They're in contact with solvent, water, but they're less likely to be polar or charged if they're in contact with water? Doesn't make any sense, right? In fact, the sentence itself doesn't make sense. Okay, arg, val, glue, ser, glue, you get the idea, is a likely repeat in the alpha helix of carotene. So these two are ones that you would have to, they can't both be true, right? You'd have to choose one versus the other. The easiest way to deal with this is, well, there's actually a few ways here, okay? You could see which is more likely to be an alpha helices. Remember that table we talked about? The other way to do this is go along. We have A, B, C. Well, C and B should probably be something that's hydrophilic, right? And so we would look at C and B, at ASP or val. Okay, so asparagine, no. Aspartic acid, that makes sense to be with water, right? Let's see here. What is this? C. Was I looking at C and B? Yeah, B. So I need to do B then. That has an OH. That makes some sort of sense, right? At least it won't be hydrophobic and then exposed to water. Okay, so we look down here, val and glue. Don't look very hydrophilic, does it? Would that make sense to expose to water? Nah. Okay, so that's probably not right, is it? So that doesn't make any sense. The alpha helix of the coiled coil is wound less tightly than predicted for an alpha helix. An alpha helix is wound less tightly. Why would that be? It's kind of a weird statement in general, right? And you'd expect if you're a structural molecule, well, you want a rope to hold. Do you want a loose rope? Or do you want a tight rope? Tight, right? It doesn't make sense, does it? Yeah, it's kind of a weird thing. It's a sentence that doesn't make sense. So do you guys have any questions There's sort of multiple levels you can tackle problems. The more memorization you have, the less thinking you have to do, right? The less memorization you've done, the more thinking you have to do. Okay? Because again, it is logically going to follow everything you've learned about chemistry, right? Okay.